Let me start with something simple, something that seems obvious but actually isn't. Before Einstein came along, everyone thought they understood how velocities work. If I'm on a train moving at 60 miles per hour and I throw a ball forward at 20 miles per hour, what's the speed of the ball relative to the ground? Well, obviously 80 miles per hour. You just add them up. That's called Galilean relativity, named after Galileo. And for everything we encounter in everyday life, it works perfectly. This is what we all learn in school, and it's not wrong, it's just incomplete. But here's where things get interesting. In the 1860s, this guy James Clerk Maxwell writes down these equations that describe electricity and magnetism. And when you solve Maxwell's equations, something remarkable pops out. They predict that light travels at a specific velocity. Not light travels really fast, but a very specific number, about 300,000 kilometers per second. This was stunning. Out of equations describing electromagnetic phenomena, a specific velocity emerges naturally. Now here's the problem. If Maxwell is right and light travels at 300,000 kilometers per second, then what happens when you're moving? This is where the wheels start to come off the Galilean framework. Let's say you're on a spaceship moving toward a light source at, let's say, 100,000 kilometers per second. According to Galilean relativity, you should measure the light coming toward you at 400,000 kilometers per second. But Maxwell's equations say light travels at 300,000. So which is it? So this is not a trivial question. This is the kind of thing that keeps physicists up at night. And people tried to fix it in different ways. Some said, well, Maxwell must be wrong. Others said, well, there must be a special material filling all of space, we'll call it the ether, and light travels at 300,000 kilometers per second through the ether. So if you're moving through the ether, you'd measure different speeds depending on your direction, just like sound travels at different speeds relative to you depending on whether you're moving toward or away from the source. That sounds reasonable, doesn't it? So physicists did experiments to test this. The most famous one is the Michelson-Morley experiment. And here's what they found. The speed of light is the same in all directions, regardless of whether you're moving or not. This was shocking. This violated everything that seemed intuitively obvious about how the world works. For a long time, people didn't know what to do with this result. It sat there in the journals, kind of an embarrassment. But then Einstein came along in 1905 and said something truly radical. He said, what if we accept this? What if the speed of light really is the same for all observers, no matter how they're moving? Now, Einstein was smart enough to realize that you can't just accept this and keep everything else the same. If light travels at the same speed for everyone, then something has to give. And what gives is our concept of time itself. See, Newton assumed that time is absolute. Time flows the same everywhere in the universe. You're here, I'm on Alpha Centauri, we synchronize our watches, and we're always synchronized. That's intuitive, but it turns out to be wrong. Einstein realized that if the speed of light is going to be the same for everyone, then simultaneity can't be absolute. Two events that happen at the same time for me might happen at different times for you, if we're moving relative to each other. Let me make this concrete. Imagine we're in a lecture hall, and I have a clock at the front and a clock at the back. How do I know these clocks are synchronized? I can't just look at them because light takes time to travel. Einstein's clever solution was to imagine me standing in the middle with a light bulb. I turn on the light, and it travels to both clocks at the same speed. Both clocks receive the light at the same time. They both get triggered to read noon, and boom, they're synchronized in my frame. But here's the thing. If you're moving relative to me, you're not going to agree that those clocks are synchronized. From your perspective, because you're moving, you might receive the light from the back clock first and the front clock second. And since both events were simultaneous in my frame, but not in yours, you'd say they happened at different times. That's not a problem with the clocks or my measurement. That's a fundamental feature of reality. Simultaneity is relative. Now, once you accept this, everything else flows from it like a beautiful logical chain. Einstein wrote down the Lorentz transformation equations, which tell you exactly how space and time coordinates transform when you move from one reference frame to another. And these equations have a very special property. They leave the speed of light invariant. That means no matter which reference frame you use to measure light, you always get the same speed. This is where it gets really interesting. The Lorentz transformation comes with a factor, gamma, that depends on your velocity relative to someone else. Gamma equals 1 over the square root of 1 minus v squared over c squared. Now, as your velocity approaches the speed of light, gamma goes to infinity. And this matters because according to relativity, the kinetic energy of a moving object is proportional to gamma times the mass times c squared. So as you approach the speed of light, the energy required to accelerate you further and further approaches infinity. Think about this physically for a moment. To accelerate something to the speed of light, you'd need infinite energy. It's not just that we don't have that energy, it's that infinite energy is impossible, so nothing with mass can actually reach the speed of light. The speed of light becomes an absolute speed limit that nothing with mass can reach. But light itself travels at the speed of light. How does that work? Well, light has no mass. For light, that energy equation works differently. Photons are massless particles, and for them, the entire energy-momentum relationship is built around traveling at exactly c. They can't travel at any other speed. Light is special because it's the only thing that can actually travel at this universal speed limit. Now, you might ask, why is this the case? Why is there a number c that nothing can exceed? And that's the deep question. The answer is actually encoded in something fundamental, the structure of spacetime itself. Einstein's special relativity is built on the idea that spacetime is not three separate dimensions of space with time tacked on as something different. Instead, space and time are unified into something called spacetime, and they're woven together by this particular speed c. Here's a way to think about it. In Newtonian mechanics, the distance between two events in space is absolute, and the time between them is absolute. But in relativity, neither is absolute individually. What is absolute, what all observers agree on, is something called the spacetime interval. The spacetime interval between two events is defined as c squared times, the time difference squared minus the spatial distance squared. This quantity is the same for all observers, no matter how they're moving. It's the fundamental invariant of relativity. And here's the beautiful part. This interval depends on c, the very structure of space-time. The way space and time are unified depends on this particular speed, and this speed emerges naturally as the maximum speed of causality, the maximum speed at which information or influence can propagate from one place to another. In some sense, c isn't chosen. It's not like someone picked an arbitrary number. The structure of the universe essentially defines what c has to be, and then nothing can go faster than that. Let me tell you another way to see this. In classical mechanics, if I have an object with mass m and I accelerate it to a velocity v, its kinetic energy is 1/2 mv squared. That's what you learn in high school. But in relativity, the energy is gamma times mc squared, where gamma is that factor I mentioned earlier. Notice that this isn't 1/2 mv squared. It's something completely different. And if you expand gamma in a series for small velocities, the first term you get is mc squared, and the next term looks like the classical kinetic energy. This means that even at rest, an object has an enormous amount of energy, mc squared. This is perhaps the most famous equation in all of physics, and it tells us something profound. Mass and energy are interchangeable. They're different forms of the same thing, and this deep connection between mass and energy is completely tied up with the speed of light. Why? Because the equation is E equals mc squared, not E equals m. The speed of light is built into the very relationship between mass and energy. This isn't accidental. This is telling us that c is fundamental to how the universe works at a very deep level. Now let's think about what it means that nothing can travel faster than light. In special relativity, we divide the world into three regions based on the space-time interval. If two events have a time-like interval, they can influence each other. Information can travel from one to the other. If they have a space-like interval, they cannot influence each other because it would require traveling faster than light. And events that are light-like separated, they're connected by light itself. This structure, this division of space-time into regions of influence and non-influence, is built into the very fabric of reality. It's not a limitation we imposed. It's a feature of how space-time works. The speed of light is the boundary between the possible and the impossible. And here's something that really blows people's minds. This speed limit isn't just about motion, it's about causality itself. The speed of light is the ultimate barrier to causality. If something could travel faster than light, you could send a message to your past. You could create paradoxes. You could kill your grandfather before your father was born, which would prevent your existence, which would mean you couldn't go back to kill him, which would mean you would exist. It's a logical contradiction. The fact that nothing can travel faster than light isn't just a mechanical limitation. It's actually a logical necessity for the universe to be self-consistent. It's a requirement for causality to make sense. Let me come back to something I mentioned briefly but want to emphasize. The speed of light emerges from Maxwell's equations. When you write down the equations of electromagnetism and you solve them, light pops out. The wave solutions to Maxwell's equations travel at a speed determined by the permittivity of free space and the permeability of free space. Two numbers that describe how space responds to electric and magnetic fields. When you multiply one by the other and take the inverse and the square root, you get c. This suggests that c is not something imposed from outside. It's not like God said, I'm going to set a speed limit. Instead, c emerges from the fundamental properties of space itself. Space has certain properties, permittivity and permeability, and those properties naturally give rise to this maximum speed. Now Einstein took this further. He showed that if the speed of light is truly universal and truly the same for all observers, then gravity itself can't be a force in Newton's sense. Gravity must be geometric. It must be the curvature of space-time. And indeed, that's what general relativity says. Gravity is not a force pulling on you. It's the curvature of space-time that you follow when you move freely. In general relativity, massive objects curve space-time around them, and other objects follow the curved geodesics, the straightest possible paths through that curved space-time. And the speed of light remains the ultimate limit even in curved space-time. Nothing can travel faster than light, even when space-time itself is curved by gravitational fields. There's something profound here. The speed of light isn't just an accident of the particular formulation of Maxwell's equations. It's not just the number that happens to pop out of the math. It's intimately connected to the structure of causality, to the division of space-time into regions of influence, to the equivalence of mass and energy, and to the very geometry of space-time in the presence of gravity. In some deep sense, we don't understand why space and time are woven together in this particular way, why the universe has this metric structure with Minkowski space-time as its foundation. But it does. And given that it does, the speed of light naturally emerges as the maximum velocity, as the barrier that cannot be crossed by anything with mass, as the speed at which massless particles must travel. Some people ask me, well, couldn't there be particles that travel faster than light? Maybe there are things we don't know about? Technically, such particles are called tachyons, and they've been proposed theoretically. But here's the thing, if tachyons existed, they would imply that you could send messages into the past. They would violate causality, and while we can't prove with absolute certainty that such particles don't exist, we have extremely good reasons to believe they don't. The universe is self-consistent. Causality works, and that's only possible if nothing travels faster than light. So when you ask, why is light speed the limit? The answer isn't just because the math says so. The answer is that the speed of light is the speed of causality itself. It's the maximum rate at which the universe can communicate with itself. It's woven into the very structure of space-time. It emerges from the fundamental properties of space, and it's essential for the universe to be self-consistent and logically sound. Einstein showed us something remarkable. He showed us that the universe isn't constrained by arbitrary rules. Instead, it's built on a few fundamental principles. The principle that the laws of physics are the same in all reference frames, and the principle that light travels at the same speed for all observers. From these two simple ideas, everything else follows. Time is not absolute. Space is not absolute. They're woven together. Nothing with mass can reach the speed of light. And yet light itself travels at exactly this speed, and this is not a limitation. This is how the universe is built. This is what the universe is. Thank you.